Hello everyone. Previously we had discussed on the merge sort, right? So today we'll be discussing on the quick sort. So let's get into the definition part first. So quick sort is an in-place divide and conquer sorting algorithm that picks a pivot, right? So it picks a pivot element and partitions the array so values lesser than the pivot come before it and values greater than come after it, right? After the pivot. So it then recursively sorts the left and right partitions until the whole array is sorted. Simple, right? So again, I'll just read this one out. Just listen to this carefully. So quicksort is an in-place divide and conquer sorting algorithm. So this is a divide and conquer sorting algorithm. Basically it is an in-place divide and conquer sorting algorithm, right? So and this one merge sort is not an this one in place, right? So we know this. That's the main difference between the quicksort and the merge sort. And what does the quicksort to do here algorithm? So it picks a pivot element and partitions the array so value less than the pivot come before it and values greater come after the pivot element, right? So this is the main approach basically. It then recursively sorts the left and right partitions until the whole array is sorted, right? So let's go with the explanation part here. First thing is divide and conquer. So quicksort divides the problem into sub problems, right? Into two sub problems basically, left and right of the pivot by partitioning around a pivot element. This one we know. This, I hope this is clear. First point. And what is the partition step here? So we have to choose the pivot here, right? So we have to choose the pivot. This is common simple choice, last element, right? We have to rearrange the elements so elements are less than or equal to pivot go left and elements greater than the pivot go right. So we will be rearranging the array so elements less than or equal to pivot go left and the elements greater than this one pivot go right. Then we will place the pivot between them, right? Simple, right? So what about the recursion part? So we will recursively apply quicksort to left and right subarrays, right? After this one placing the pivot, so what we will be doing, so we will recursively apply quicksort to left and right subarrays, right? So excluding the pivot which is now in the correct place, so we will not be considering the pivot, we are excluding the pivot. Just keep this in mind. So what will be the, so this is what we will be doing, this is what we will be doing. So this one we will be implementing or articulating the same thing in the form of code or the algorithm. So let's see that when we consider the algorithm. So what will be the complexity here? Or average time, this one complexity would be big of n log n. In the worst case it would be big of n square when pivot choices are poor basically, right? So when they are already sorted, this one input and picking the last element, right? So space complexity would go to this one big of logarithmic n. So this will be average for the recursion stack because big of recursion stack can go up to the big of n depth, right? So in the worst case we know this. And this is in place, right? So but not stable because the common in place or her partition sort without extra arrays, but it does not preserve relative order of the equal elements, right? So this is not stable. And one more thing, pivot choices, about the pivot choices and the optimization, this also I wanted to discuss basically. So this also I have considered, this is one of the important points. So we will be making use of the randomized pivot or median of 3 to avoid the worst case patterns, right? So this one we have to keep in mind, this is important as well. So we will be going with the, or we will be using the randomized pivot or median of 3 to avoid the worst case patterns. We will be switching to insertion sort for small subarrays and we will be going with the tail recursion elimination, right? So that can reduce the stack usage basically, right? So the same thing, let's see that one in the form of algorithm or the code. First what we will do, so here let me go with the example array first that we have to sort, right? So let's go with the initial unsorted list. So I'll just go with array equals 3, 6, here some random numbers 8, let me give 10, 1, 2, 1, this is fine. Some random numbers I have given. Let's go with the this one print. So let's print the original array first, right? So I'll just go with original array. So this is fine. Now let me pass the array. Yep. Now let's do one thing. Let's partition the function first. Let's go with the partition function. Sorry. So this is nothing but Lomuto partition scheme. So this name is good. Lomuto partition scheme. So let's go with this one, partition helper function, or this one, partition function in simple terms, right? So I'll just go with def partition. This is fine. So let me pass a along with this low comma high. This is fine, man. Now let's do one thing. We have a list, low start index and high end index, right? So let's go with the pivot now. We have to choose the last element as the pivot or the pivot. So this one will be pivot equals a of high. This is fine. Now let's assign I to low minus 1. So this is also fine. So let's go with the for loop, meaning let's iterate from low to high minus 1. So here this would be for j in range. So this one low comma this one, what do we call, high, right? So this is fine, low comma high. So within the for loop, let's go with the simple if condition here. If the current element is less than or equal to pivot, it belongs to the left side. We know this one, right? So I'll just write it here. If a of j, if it is less than or equal to pivot, then it belongs to the left side, meaning we have to move the boundary for smaller elements. So this will be I equals I plus 1. Now we have to swap the current element into the smaller than pivot region, right? So how can we write that one? So I'll just give here a of I comma a of j. So this one will be equivalent to the a of j comma a of I. This is fine. Now let's do one thing. We have to place the pivot after the last smaller element. So this will be a of I plus 1 comma a of high. So this one will be a of high also a of I plus 1. This is fine, man. Finally let's return the pivot final index. So this one will be return I plus 1. So this is fine, man. Yep. Now let's go with the quicksort recursive function, right? So I'll just go with recursive, or let me go with a quicksort. This is enough. Yep. Quicksort, let me pass a comma low comma high. So this is fine, man. Now let's do one thing. Let's go with the base condition when there are at least two elements, meaning if low is less than high. So this one, if low is less than high, this is fine. Now if low is less than high, let's go with the partition. This one, let's partition the array and get the pivot index, meaning so this one will be p equals so let me pass the partition function here, partition of, let me pass a comma low comma high. So this is fine. Now let's go with the quicksort here, quicksort of a comma low, this one comma p minus 1. Also we have to recursively sort the right partition as well. So I'll just go with a quicksort here. So this one will be a comma p plus 1 comma high. This one is fine, man. Fine. Yep, this one is fine. So now let's do one thing. Let's call the quicksort on the entire array, meaning I'll just go with a quicksort here. So this one will be array 0. This one is length of array minus 1. So we are sorting in place here. We know this, right? So finally let's print the final sorted array. So let's go with the print for the interactive purpose. So I'll just go with sorted array here. This is fine. So let me pass the array here. So we have to print the, or we have to show the result of the quicksort, right? So this is fine, man. So this is it for the code basically. So the output that we need to get here is, first we are printing the original array, this one 3 6 8 10 1 2 1. So the output that we need to get here is 1 1 2 3 6 8 10 in the ascending order, right? So this is fine. So let me explain whatever I have written first, then let's do one thing. Let's try to run the code. I'll just explain the output rather, right? So this, I hope this is fine, man. We have just implemented the same thing whatever I had explained earlier, right? So this is fine. Now I'll just come here. It's fine. Let me press Ctrl J. So this is Python. So this one right click, rename this one, control C dot py. So here original array and the this one we are not getting sorted, right? So somewhere I have missed something. 13681. So we have to get here 1123681, right? So we are not getting the correct output. Let's see what we have done wrong. So I believe the code is correct, but we have the indentation problem, I think. So we have to move this one here, I believe. Let's check the same if this works. So we have to move this one, right? So we are writing this one within the if condition basically. So this will be wrong actually. So now let me run this one again. Yeah, now we are getting the correct output. So yeah, this was indentation problem basically. We had written this one within the if condition. That is the reason we were not getting the sorted array basically, right? So now we are getting this one original array 368 ton 121 whatever we have given, and the sorted array 112368 ton. So here let me explain the output. So here this is the input we have provided basically, right? So the first one, the original array. So this shows the unsorted list before the quicksort runs, right? So this is nothing but the good demo array. We are often including the duplicates as well, right? Just to show how equal elements are handled here. So, and this is nothing but the sorted array, right? This is the array after the quicksort is finished, or quicksort gets finished basically. So every element is now in the ascending order. We know this. Both ones ended up at the start. See here we have 1 1, right? So we have considered the duplicates as well. Both ones ended up at the start. This is fine. This is it basically. Order among the equal elements may differ from original because this one standard in place quicksort is not stable, right? So this is fine. Now this is it for the output. We have got the correct output, right? So, or the desired output basically. So this is it for the quicksort. Very simple, right? So now let's do one thing. Let me summarize whatever we have learned so far. So just keep these 3 or 4 this one points on the mind. So quicksort, this one, we'll be making use of the divide and conquer also. So we'll be going with a partition by pivot and recurse, right? So then let's discuss about the average time. So this one would be big of n log n, and the worst case it would be big of n square. So we have to avoid by good pivot choice, right? So this is one thing. And also this is in place, right? So this sorting takes place, this one sorting takes in place, and this is fast in practice, right? But not stable by default. So this is not one of the stable algorithms among the quicksort, right? So the sorting takes place in place, and this will be fast no doubt, but it is not stable by default. So we will be making use of, or we had made use of, the randomized or the median pivot and hybrid approaches on production, right? So this is it for the quicksort. Just keep these things in the mind, right? So this is it about the quicksort. So previously we had discussed about the merge sort, and today we had discussed on the quicksort. Next we'll be going with a heap sort, right? So next we'll be discussing on the heap sort. For now this is it. Thanks for watching guys.